So basically in section 8.4 here, we're going to look at some relationships that exist between different trig functions, and there are four different types. Reciprocal relationships we'll start with, look at one of those. Relationships involving negative signs, and again we've looked at some of these already, actually both of these already, we're just going to kind of formalize them now. Pythagorean relationships with trig, and also co-function relationships, the sine, cosine, tan, cotan, secant, cosecant. Talk about why perhaps those trig ratios are named the way they are. So we'll look at one of each type, and in section 8.4 in your text, you got lots of boxes, 4 boxes on 2 pages, and you do need to keep track of these formulas, and you want to not just memorize them blindly, but you want to understand where they come from, and then it's pretty easy to keep track of them all. So let's begin here with one from a reciprocal relationship. So if we consider here cosecant, we remember in standard definition, our definition for the cosecant of an angle is, we have our angle, we have a point on the terminal side, and our cosecant by definition is going to be, let's see, it would be r over y. And that's our definition of cosecant. So therefore, if we want to consider the reciprocal of r over y, the reciprocal of r over y is y over r. And by definition, y over r is the sine of theta. So therefore, cosecant and sine are reciprocal trig relationships, reciprocal trig functions, reciprocal trig expressions. And you've noticed that before in our previous work when we first introduced our definitions for cosecant and sine. We saw that those were reciprocals. And we simply now formalize it. So you're going to have reciprocal relationship secant and cosecant, and reciprocal relationship tangent and cotangent. So to see our relationship with negatives, we've already looked at them to some degree, and we're now going to formalize what we're doing. Suppose I've got an angle theta, and we'll make it a first quadrant angle. Terminal side lies in the first quadrant. If I look at theta and I then consider what negative theta down here, what would the coordinates be for the terminal side of negative theta? And the answer would be still x and negative y. So if I wanted to look at, for example, how does the sine of negative theta compare to the sine of theta, and the answer would be those two values are opposites. And so my relationship with negative, the sine of negative theta equals negative sine theta, or the negative sine, the equivalent negative sine of negative theta equals sine theta. So that can be done with sine. Now obviously we note that with cosine, the x-coordinate won't change here, so my co-relationship, my negative relationship with cosine is the cosine of negative theta is the same as the cosine of theta. Now tangent is y over x by definition, and so our tangent of negative theta equals the negative tangent of theta. And those are our relationships, some of our relationships with negatives. And there are others, and you want to figure out what the secant, cosecant, and cotangent relationships are, thinking that they're simply the reciprocals of your sine, cosine, and tangent. So I'll let you think about that, and that's again the box on page 317. Take a look. So let's suppose we have our angle theta here in standard position, and we do have the point xy in the terminal side actually in the unit circle. So our radius here, our length here is 1. What do we know? Well, we know by definition our sine of theta is y, and our cosine of theta is x. And if we zoom in here on our figure here, and we look at that x and that y and that y and that 1, again looking at our over x up y, zoom in on that, we've got a right triangle, and obviously x squared plus y squared equals 1 squared. We know x and y are sine and cosine, so therefore cosine squared x plus cosine squared theta plus sine squared theta equals 1. And so that's the most fundamental Pythagorean identity. From that, we can derive two other Pythagorean identities. If you look at the sine squared theta plus cosine squared theta equals 1, take a look at the box on page 317. How do you get to 1 plus tan squared theta equals secant squared theta? Well, how can you get secant squared out of this equation somehow on one side? Answer, if I had a 1 over cosine squared, that would do it. So let's go ahead and divide everything in this equation by cosine squared and then simplify. What's sine squared over cosine squared? Well, in this case, sine is y over cosine squared is x, and y over x, we remember, is the tangent, so that's going to be tangent squared theta plus, well, cosine squared over cosine squared equals 1, and 1 over cosine squared equals secant squared theta. So dividing our original here, cosine squared plus sine squared equals 1, if we divided through by cosine squared, we generated a second Pythagorean identity. And what do you think we're going to do? What are we going to divide by? What are we going to divide by on cosine squared plus sine squared equals 1 to generate the third Pythagorean identity? I'll let you figure that out on your own. So let's suppose we have here an angle theta, first quadrant angle, terminal side. I'm out here R, point the terminal side XY. What's the measure of this angle going to be right here? Well, it's going to be equivalent to this angle here, obviously. If I drop a perpendicular, those are parallel lines. Alternate interiors are congruent. I also know, though, that in this right triangle, I've got three angles that add up to be 180. So if this is theta, and that's my right angle, that's going to be 90 minus theta. Alternate interior angles congruent. This is 90 minus theta as well. And let's suppose we take that angle, that 90 minus theta angle, and we put that in standard position. If I'm over here with this right triangle here, and I label, I've got x, x is going to be opposite that 90 minus theta angle. And so that's my x here, coming out x, going up y. Let's put that 90 minus theta into standard position and label the points that are r, point on the terminal side, r units out. What would those coordinates be? Well, this right triangle right here is simply going to get, the sides are going to get switched, as we've seen before. So now I'm going to be having here a y and an x. If I came out over here, if this is theta here, y is opposite the theta, and 90 minus theta here, x is opposite the 90 minus theta here. If I then take that angle here and put it down in standard position, I'm simply going to reverse the y and the x. So we got our right triangle here. Let's then look at what is the, and if this is, those get reversed, we've got here an y and an x. We'll actually label it out. So the sine of theta then is going to be y over r. And how about the cosine of 90 minus theta? That also is going to be y over r. Well, transitive property, if two things are equal to the same thing, then they're equal. Therefore, sine of theta equals the cosine of 90 minus theta. And again, I could have done this in radians, pi over 2 minus theta. And I look at that relationship and I note the following. These angles right here, theta and 90 minus theta, are complementary angles. And complementary begins with the word CO. So that might be a little clue as to why the cosine is called, or the cosine is the cofunction for sine, because there's a relationship between the sine and the cosine of complementary angles. Now I did this with an angle, an acute angle in standard position in the first quadrant, and we looked at right triangles. Certainly it was convenient to look at our right triangles, but this cofunction relationship will hold for angles theta that are negative, positive, what have you. You can have your angle here, theta, being 150 degrees or 400 radians or whatever. The relationship will hold. For example, sine of 120 equals the cosine of 90 minus 120. But to illustrate why it works for you guys, I just want to persuade you by a very specific acute angle theta in that first quadrant. So what are you going to be asked to do? Why do we have these formulas? Well, they're going to help us simplify expressions at times. One strategy to simplify a trig expression that looks fairly complicated is you can think about either reciprocal relationships, or you can think about converting things into just sine and cosine and seeing if things cancel or simplify. So the first thing I'm going to do, the instructions for a problem like this would be simplify this expression. And you say, okay, well, sine theta, that's about as simple as it gets. I could write that secant as 1 over cosine theta, and the cotangent is cosine theta over sine theta. And I notice then that multiplying numerators and multiplying denominators, I'm going to get things to cancel, and I'm going to end up with 1. So this expression right here is equivalent to 1, except not always. Why not? Well, the original expression, you notice cotan theta has in its denominator, it has a sine theta, and secant has a cosine theta. So wherever this expression is undefined, the whole expression is undefined. So clearly I can't have I can't have a 0 in the denominator. So cosine theta can't be any multiple of pi over 2. And I can't have sine theta being 0 in the denominator. So I can't have any angle with a multiple of pi, 0, pi, 2 pi, negative 2 pi, etc. So this expression up here is only defined for all angles that aren't coterminal with a multiple of pi over 2 or pi. And it does equal 1, this expression. I can put in whatever I want for theta except for the values where the expression is undefined. And when I do that, I will always get a 1 out. And this is called a trig identity. We would say for values where this expression, sine theta times secant theta times cotan theta, the values where this is a defined expression, that expression upon simplification equals 1. So this one's a little trickier because it's going to involve both a cofunction relationship and a Pythagorean relationship. I look at this at first glance and I say, this must be pretty easy. 1 plus tan squared is secant squared. The problem is right in here, though. That cofunction relationship is a 90 minus x. So I've got to deal with that first, and that actually is a bit tedious here. So I can say, how can I get a 90 minus x out of this? Well, if I factor a negative sign out, then I can get a 90 minus x in here. And then I can say, okay, well, basically I've got then 1 plus tangent of negative 90 minus x quantity, all of that squared. And now I want to look at what's going on in here. I have a tangent of some angle, and the tangent of some angle is the tangent of the negative of some angle is going to be negative of the tangent of the angle. So I can rewrite this as 1 plus negative tangent of 90 minus x quantity squared. Now, on we go. I've got in here the tangent of 90 minus x, and I know that's cotangent of x, cofunction relationship. So I have a 1 plus negative cotangent of x quantity squared. And on we go. I then say, okay, negative cotangent squared is 1 plus cotangent of x squared, and that is a Pythagorean relationship. 1 plus cotangent squared is cosecant squared of x. That's about as tough and nasty a simplification that you're going to have. And again, you really, the instructions are going to be simplify, and note that we were able to go from an x minus 90 all the way down to something just in terms of x. And when they say to simplify, if you've got x minus 90s, you want to get rid of them and get down to just x's. So the other type of problem we're going to get in this section is, it's a mouthful, but you're going to be asked to prove a trigonometric identity. What does that mean? Well, you're going to be given an equation, and you're going to be asked to prove that the equation is true. And on one or both sides of the equation, you're going to have some constants and trig functions. Now, it actually is implying that the expression is true for all values a, all values of the variable, where the expression is duly defined. Now note, if the secant of a here equals 1, this expression isn't defined. Or cotan, remembering, is cosine over sine, where the sine equals 0, this expression is not defined. So wherever, for all other values of a that each side of the equation is defined, your trig identity states then that left side equals right side. Well, how can you prove a trig identity? Well, one way is you can take the complicated side and make it simpler so it appears like the simpler side. Another way you can prove a trig identity is take one side, make it simpler, take the other side, make it simpler, and if the two simple things are equal, then by the transitive property, the two more complicated things that they came from would be equal. Strategies in doing this? Well, one strategy is if you've got clearly it's better to take the complicated side and simplify rather than build the simpler side up into something more complicated most of the time. And so looking at how to simplify this, we've got a couple options. I'd mentioned in the earlier slide that maybe converting everything to sines and cosines and coming down might work. But I also look at this expression and say, hey, I can get a common denominator out of that. And when I get a common denominator, things might simplify. Things might cancel, and I might get a cotan, a cosine squared over sine squared, or a cotan squared. So let's see what happens if we go at, again, looking at the complicated side, trying to simplify it, and we're going to find a common denominator and see what happens. My common denominator here is going to be a 1 minus secant a times a 1 plus secant a. And to get that common denominator here for the first fraction, I'd have to multiply by 1 plus secant a over 1 plus secant a. So I'd have a 1 plus secant a here. And to get a common denominator here for this one, I have to multiply by a 1 minus secant a over 1 minus secant a. So that's going to be plus a 1 minus secant a. And when I do identities, I like to put a little question mark over my equal sign until I get to the last step, and then I put a check when two things are clearly equal. And I can use a ditto mark for the side that I'm going to leave alone as I move down and do my work. So far we are to there. Great. Numerator simplifies pretty simply. 1 and 1 is 2, and secant a and negative secant a are gone. Well, that's looking pretty good. We got a 2 over here. I note that the denominator, when I multiply it out, it's going to be difference of the squares, a minus b times a plus b, so I get a 1 minus secant squared of a, and I'd ask, does that somehow equal negative 2 cotan squared of a? And I look at that 1 minus secant squared, and that's looking like a Pythagorean, something involving a Pythagorean identity. So let's think about that. I'm going to let you think about that for a minute. I do know that if you thought about it a little, hopefully you've thought about it the following way, that my 1 plus tan squared theta equals secant squared theta. And so if I want a 1 minus secant squared, I would move the secant squared over here, the tan squared over there, so I'd get 1 minus secant squared theta equals negative tan squared theta. So I can then come over here and simply plug in that negative tan squared theta to be my denominator. And I then remember that the tangent and cotangent are reciprocal, so if I've got the tangent in the denominator, I can use that reciprocal relationship then to write this as 2 cotangent square root of theta with the cotangent up in the numerator and move the negative sign out front, and I then have matched up with the other side. Now, at this point right here, could I have written this in terms of sines and cosines and simplified and gotten a 2 cosine squared over sine squared? Could I have taken this and brought it down and written this as a 2 cosine squared over sine squared? Sure, I could have done that. But again, if you know your Pythagorean relationships, you don't need to always convert to sine and cosine.